A circular swimming pool has a diameter of 24 feet with the sides 5 feet high and the length of the water is 4 feet. How much work is required to pump the water over the side? So let's draw a picture first and set up an axis. So there's our swimming pool, and we got 24 feet, and then it's 5 feet high, and we got water up to 4 feet. So let's set up an axis. We'll say that at the top is our 0th position when the water goes off the top, and since the whole thing is 5 feet long, that's 5 feet, so right here, since I have 4 feet of water, that division is 1 foot. So between 1 foot and 5 feet, I got 4 feet of water. So set up an axis, then go through the steps piece by piece to figure out the work done on a slab that you're looking at. So we're interested in the ith interval and how much work is done in just lifting this piece out over. And in the ith interval, I'm going to start with volume of that one piece in that interval, and volume of that one piece, since it's circular, is pi r squared h, and the radius we know is consistent throughout, and it's 12 feet. So pi 12 squared, and the height of this thing we know is delta x. So that's in cubic feet, or volume. From there, we try to get the mass, or maybe the force, of that one little piece on that one little piece. So we're going to need to use the density given of whatever liquid it is that we're dealing with. So just focusing on this one piece only, the work, our goal is to get to work done on this one piece and then add them all up. Density of water is 62.5 pounds per cubic feet, and the volume of that one piece only we looked at up here. Just multiply that out, it's 144 pi. So notice the cubic feet cancel and we end up with 9,000 pi delta x pounds. This is already a force. So the force acting on that ith interval is what we just calculated above in pounds. Had this been in metric units, we would deal with it differently and multiply it by 9.8 meters per second squared to change it to a force of newtons. But in this case, we already have the force on that one piece in the ith interval. Now we need to get the work done on that one little piece. So work on that one little piece is the force on that one little piece times the distance that piece moves. We already know the force from previous step in pounds, and we need to get the distance. So go back and focus on that one representation you made and figure out what the distance is that it moves. So that little piece, or everything in that small interval, approximately moves up over the side that much distance. So what is this distance? That's just an x distance from 0, where I labeled x equals 0, all the way to whatever this is. If I go all the way down, it's 5. If I go up to here, it's 1. But if I go up to some random variable place, that's just going to be xi if I'm going into the ith interval. So my distance moved is xi, and this will lead me to the integral. So force acting on that one piece right here in pounds, the distance that one piece moves is xi feet. Depending on which representation I'm looking at, it's different xi that it moves. I put that back into my integral, so I have 9,000 pi delta x, that's my dx in my integral, times x. And now I have to go back on my picture and see the little representations that I was making, what interval did they cover based on the way I've labeled my axes. So it looks like it's between here, and based on my axes, I'm going down for the positive direction. I'm going from 1 to 5. So between 1 and 5 in my picture, based on my axes, is where I actually have water to move out. Now we will go ahead and integrate this, and this will account for all the different pieces that I am supposedly looking at and adding up all the work done on each of the little pieces. I'm doing it all here with the integral representation. So I'm going to pull out my constant, and my integral is actually not that bad at all. I have 9,000 pi x squared over 2 from 1 to 5. And once I integrate, it looks like I get 339,292 foot-pounds. And notice even when I was looking at the little pieces, or the work on the little pieces, it was pounds and feet, and everything works out okay. So I end up with that much foot-pounds of work required to move all the water out over the side. I also want to quickly go over what would happen if you set up your axes differently. Nothing should really change, and the amount of work done should still be the same. So we still go get our volume of that one piece, that one representation. Nothing is different in that step. Second and third step I've done together, trying to get the mass of that piece or the force acting on that piece. Still, you multiply the volume and the density to get your pounds. What's different is what happens in step 4. So the force we have from above, that many pounds. The distance is what you have to be careful about. That's going to look different, because now I have this one representation in blue. I'm going to move it up over the water. So here is the distance di that one piece moves up to go over the side. And notice that distance is no longer x, because it's not touching my origin in this case. My origin, or my 0th location, is down here. So what I really have is, this is my x, because it goes all the way down to the origin. This piece that I'm looking at in green is actually the entire distance, 5, minus this little x. So the distance moved in this case is actually 5 minus x feet. That's what changes in this case. So what I end up with in step 5 is the integral. I have my 9,000 pi. Now I have 5 minus x involved, and my delta x dx. I've got my foot-pound going on. The other thing that also changes is, notice you're looking at your representations and you're looking at your weight in the different pieces. In which region based on your axis? You're looking at those pieces right here, and that, according to your axis, is from 0 to 4 this time. So positive is in the up direction in this case, and you're going from 0 to 4. Notice how that integral is different than this integral, because our axis was different. The distance here was x, and our water was contained based on our axes from 1 to 5. Here, if you set up your axes differently again, the water is contained between 0 and 4, and the distance moved is that dangling segment in green up there, which is actually 5 minus x. And if you go ahead and integrate this, you will get the exact same amount of work done. Notice you'll have to do a little bit more. It's a polynomial, 5x. X squared over 2 from 0 to 4, and once you punch in your limits and multiply it by 9,000 pi, you're going to get the exact same amount of work that was done by looking at it this way. So either way you set up your axes doesn't matter. The key thing is to pay attention to the distance that one representation moves to go over the side, and also pay attention to where the water is contained so that you can label your limits accordingly in both cases.